Nuclear chemistry is where chemistry gets weird. Because most reactions that we deal with electrons, but nuclear reactions involve an actual change to the nucleus, hence the name nuclear. Okay, and so they come in two flavors. We have radioactive decay, where, as the name kind of implies, they get smaller. The nucleus gets smaller. Or we can have what we call nuclear transmutation. Big wordy name. That basically that's where atoms gain and their nucleus gets bigger. And so there's two varieties. Either the nucleus can get smaller, that's decay, or the nucleus can get bigger. Okay. All right, so elements in a nuclear reaction are written with the atomic mass and the atomic number, like we just saw in our previous lesson. So I've got uranium-238. So uranium has an atomic number of 92. It has an atomic mass of 238. When you're making a nuclear power plant or a nuclear bomb, you want uranium-235. That's the one that reacts the best nuclear-wise. And so you look there. So there are also 5 elementary particles that are common in nuclear reaction. They're also written in the same way, that on the bottom is the atomic number and on the top is the atomic mass. So a proton has a number 1 and a mass of 1. Neutrons have no protons and a mass. And then we have electrons. We write them as having a negative atomic number. And when electrons are being emitted, they are called beta particles. That's why we have the Greek letter beta here, with a 0 and the -1 there, just like an electron. And then we have what are called positrons. Positrons are the antimatter form of electrons. That sounds crazy, but it's true. Antimatter is real. It does actually exist. However, it just doesn't exist for very long. In a world full of matter, it gets annihilated very quickly. But that is a topic for another lesson. And then finally we have what we call alpha particles. We saw that with Rutherford's experiment, trying to find the nucleus, not trying to find, where he found the nucleus of the atom. And so we have alpha particles, which are, like I said, it's the nucleus of a helium atom. So it has an atomic number of 2 and a mass of 4. So nuclear reactions are balanced using the atomic numbers and atomic masses. They have to be the same on both sides, or the sum of them has to be the same. So for example, I've got a form of hydrogen, an isotope of hydrogen called deuterium, that has a mass of 2 and 1. So I've got 2 and a 1 over here, so this needs to be a 1. This is 1 and 1, that's already equal, so this has to be a 0. Okay, so 1 and 0 gives me a neutron. Looking at copper, it goes from 61 and 29, and it loses a beta particle, it loses an electron. So 29 and -1 gives me 30. But because I've changed the atomic number, the identity has changed. The mass is still 61, but because I've changed the atomic number, I'm no longer copper, I am now zinc. Okay, this is like every alchemist's dream, that we can actually change one type of atom into a different type of atom in a nuclear reaction. And so because the atomic number changes, so does the actual identity of the element. We see the same thing again here with polonium 84, and it drops down to 82, which means we're giving off something that's got a 2. The mass drops 4, okay, and that gives us alpha particles. All right, so nuclear stability. There are 2 forces affecting the stability of the nucleus. We have electrostatic repulsion. Remember, like charges repel. They don't like each other. So the protons in the nucleus are repelling each other. They don't want to be anywhere near each other. And then we have the nuclear force. And so in the nuclear force, the neutrons are kind of being pulled together by what are called the strong and weak nuclear forces. They're what actually keeps the protons from pushing each other so strong that they completely separate the atom. And so as we go through, with atoms less than 83 protons, there's at least one stable ratio that works. And so they tend to kind of react accordingly. if they have too many neutrons, then they try to give off beta particles in trying to get stable. So for example, carbon-14. Like I said, it radioactively decays. And so it radioactively decays and it kicks off a beta particle or an electron and changes into nitrogen. This is the normal stable form of nitrogen, 7 protons with an atomic mass of 14. If they have too few neutrons, then they'll either give off a positron or try to capture an electron. So that's what these reactions are showing. I'm not going to go into that too deeply. Okay. So we get to what's called nuclear binding energy. So in nuclear binding energy, the actual weight of an atom is less than the sum of its protons and neutrons. And so that's weird. So if you actually look at the mass of protons and neutrons individually, and you add them all up, you will not get the atomic mass. Some bit of that energy mass is going to be missing. And that mass is converted into energy by Einstein's famous equation, E equals mc squared. E stands for energy, m is mass, and then c is the speed of light in a vacuum. And so what this equation is saying, that energy and mass are interchangeable. You can convert from one to the other. Kind of blows the mind a little bit, but that's the idea there. You know, think Star Trek and teleporters or food replicators, where they take energy and transform it into matter, and vice versa. This energy that the mass is converted into is called the nuclear bonding energy, and is what holds the nucleus together. For large atoms, it can really take multiple steps before they get down to something stable. Like I said, anything smaller than 83, atomic number 83, has some stable form. Once you get bigger than 83, they're not stable. Their nucleus is just too big. There's too many neutrons, too many protons. There's too much forces going on to make a stable nucleus. And so they generally tend to decay. And so, for example, if we start with thorium, it decays to radium, then back to actinium, back to thorium, radium, radon, polonium, lead, bismuth, and tellurium. Thallium, sorry. And that decay, though, is not constant in terms of grams per year. It is, in fact, the decay is dependent upon the amount of material present. And so the way we talk about radioactive decay is what we call half-life. So a half-life is how long it takes for half of a sample to decay. So, for example, if I have 100 grams of carbon-14, it's not going to decay faster than 50 grams of carbon-14. It's not really, you can't really measure a grams per year thing. It's not like a certain number of atoms decay. It's 50% of it will decay over a half-life. So if I start with 100 grams of carbon-14, then in some period of time, I'm going to have only half of it left, so one half-life. And so after one half-life, I've dropped from 100 grams down to 50 grams. Okay? And then the next half-life, I go from 50, not to 0, but 50 to 25. Once again, I drop in half. And then one more half-life, that drops in half again, from 25 grams to 12.5. Then 6 1/4, then 3 1/8. And then smaller numbers and smaller numbers as you go further in the half-life. So each type isotope has a constant half-life, but they can vary dramatically. So carbon-14 has a half-life of 5,730 years, while carbon-15, a very rare isotope, its half-life is 2.45 seconds. So if I start with 100 grams of that, literally in under 20 seconds, I'm left with less than a gram, because it decays that fast. Where if I have 100 grams of carbon-14, I'm 40,000 years later and I still have a gram left. And so half-lives vary dramatically. Uranium-238, 4.5 billion years. That's why getting rid of uranium waste is a pain. Okay? So the constant half-life, though, has its advantages. It allows scientists to use relative concentrations of radioactive elements to accurately date objects. This is where we get radiocarbon dating. They use other isotopes like isotopes of uranium to date rocks. And so we use this to date things. That's how they get these dates for really old things. All right, fission. So in terms of big nuclear reactions, there's two. There's fission and there's fusion. So fission is when a large atom, something with a mass greater than 200, splits into two or more smaller atoms and emits neutrons. So this isn't like the other nuclear reactions we've already seen where they just do alpha particles or positrons or electrons or neutrons, that kind of thing. This is we're literally splitting an atom into two more atoms. So for example, uranium-235. When it is struck with a neutron, it will split into strontium and xenon. Both of these are stable, and so it stops, but then it gives off three more neutrons. Okay. This reaction can create what is known as a chain reaction, as each uranium-235 can initiate the fission of three others. So it takes one neutron to start the reaction, but it gives off three more. And so as it gives off those three, then we get what's called a chain reaction. And it requires what we call a critical mass to get started. So look at this. So we start with one uranium-235 reacting. And then we get 3, then 9, then 27, 81. And then after 50 reactions, we have this ginormous number. That's why we worry about nuclear meltdowns in a reactor. That's when this chain reaction gets going in a reactor without being able to be controlled. And it causes major problems. Think Chernobyl. If you're not old enough to remember Chernobyl, look it up. A Russian power plant that it melted down, and that city is still uninhabitable. All right, so that's fission. The other big nuclear reaction is fusion. So fusion is the opposite. We're taking small atoms and we're putting them together to make a larger one. So fission is splitting, like a fissure is a split in a rock. Fusion is combining, like we're fusing things together. So this is a natural process in our sun and other stars. In our sun, it takes 4 hydrogen atoms and fuses them through a series of steps. I'm not showing all the steps here. Fuses them in a series of steps to form helium and 2 electrons, or 2 beta particles. Okay. We have been trying to do this on Earth. However, the sun's kind of hot, and the amount of energy and everything, it's just massive pressure. And so we have successfully created a fusion reaction. The problem is it took more energy to contain it and start it than we got out. So we have yet to get a stable thing coming out of it. So like I said, we've used particle accelerators to make new elements, study fundamental particles of the universe, and then we use small amounts of radioactive isotopes as what we call tracers to study different parts of the body. You can take a barium milkshake to study your intestines. You can they give you a shot of radioactive iodine to study your thyroid and that kind of thing. And so with the nuclear chemistry, I put this in here because it is required by multiple state standards. However, I don't think it's that important. I don't have anything in the workbook on it other than the notes page, because it's just not one of those things. I have a chemical engineering degree and I have a degree in chemistry education, and neither of those degrees did I ever use nuclear chemistry. So consider this your exposure to nuclear chemistry. Like I said, there's nothing in the workbook on it other than a notes page. And we will move on into our next unit on quantum mechanics